Lucas Harris will be talking about the experimental GFDL SHiELD model design and forecast applications. Go ahead, Lucas.
Oh, thank you so much, Mike. And first of all, I want to thank the rest of my research team here, the FE3 team, as well as our collaborators, both in modeling systems here at GFDL and our external collaborators as well. This is actually an exciting opportunity for me. I actually grew up in the central region. I'm originally from Rockford, Illinois, and I went to Northern Illinois University before going on to Washington to get my doctorate, and then over here to Princeton and to the Geophysical Fluid Dynamics Laboratory. So thank you so much, everybody, for giving me this opportunity to speak today. So what is SHiELD? So SHiELD is a system for high-resolution prediction on Earth to local domains. And this is a what we call a unified weather to subseasonal system, which is built on the modeling frameworks developed here at GFDL called the flexible modeling system. It's used for our whole suite of weather and for especially our couple climate models that are run here at GFDL. And SHiELD is designed to be configurable for a variety of applications. So I show a number of different configurations here. We have our backbone 13-kilometer SHiELD, which is more or less like the existing GFS. We also have a coarse resolution for subseasonal prediction and a couple of nested configurations, one called SHiELD for contiguous United States, SHiELD for the tropical Atlantic, a new one called SHiELD, which uses our multiple nesting capability, and then our global storm resolving model called SHiELD, which is an exciting new thing I'll briefly discuss a little later. SHiELD couples the non-hydrostatic FE3 dynamical core to a modified form of the GFS physics and initialized from GFS analyses. So here are the particular packages we're using. In particular, we have a advanced microphysics package called the GFDL Microphysics. It's run in line within the dynamics. And we also use a mixed layer ocean to be able to represent some form of a coupling to the ocean in a relatively simplified context. A little bit about the philosophy for SHiELD. SHiELD is designed to be a relatively simple, streamlined approach to modeling and demonstrating new technologies and to aid NOAA modeling. And the big utility for model developers and users is that it's a single code with one executable and one workflow. It's a very well-designed, unified system. Going to a different configuration basically means you run a different use a different run script. And indeed, this is used to demonstrate new capabilities, especially in the FE3 dynamical core, new physics and new framework technologies that we're developing here at GFDL, as well as with our vast community of partners I'll talk about a little bit later. SHiELD is related to both the unified forecast system and the GFDL climate modeling suite. In particular, they all use the same science components. So improvements can be seamlessly transitioned from SHiELD into these other weather and climate models, as well as those in the broader FE3 community. The physics in SHiELD, as I mentioned, are a modified version of the GFS or medium range weather application physics. These are, the idea principally you're taking here is to use one physics suite for all of our applications. So we don't have a physics suite that's tied to one particular use case. Instead, it's useful for all of these different things. We have a seamless system here. Another thing we take advantage of is that we do yearly updates for most of our, especially our real-time systems. And by doing this, I'll show you an example of this a little later. We get gradual year-over-year improvements to our models that add up over time, as well as improvements in one of our configurations can then contribute to improvements in our other configurations as well. And furthermore, we contribute to a number of different intercomparisons and test beds. We contribute to the Hazardous Weather Test Bed Spring Forecasting Experiment that just wrapped up a few weeks ago. We also contribute to the forthcoming HREF real-time experiment, tropical cyclone experiment, as well as these international projects like DIMOSIC, which is run by the European Center, and DIAMOND, an intercomparison of global storm resolving models that is run by the Max Planck Institute and by the University of Tokyo. So, everything sound okay, Mike? Okay.
Yes,
great.
It does.
Okay, fantastic. Thank you. Okay, a little bit about the FE3 dynamical core. One thing I've discovered over the years is that other than other DICORE people, people really don't want to hear a whole lot about dynamical cores. So I'll limit the discussion to just this one slide. So FE3 is the dynamical core. It's a fluid solver, or more colloquially, an engine for a community of atmosphere models, both here in NOAA and NASA, used for a lot of different applications such as data assimilation, reanalysis, planetary atmospheres, climate, chemistry simulation. That's this GeoSchem community model. FE3 has also been implemented within the community within the NCAR-led, see here, what is it? Community Earth System Model, CESM, and has other applications, especially in China and Taiwan. FE3 is designed with a couple of different things in mind. It's designed to be numerically accurate and following a number of different physical principles. It's computationally efficient to the level that to the point where we can make as good utilization of computing resources without compromising the scientific integrity of our algorithm. My FE3's creator, S.J. Lin, had a good saying that a good model must be a fast model. We have a flexible solver and interface allowing to be plugged into a number of different models and developed holistically, as well as a number of advanced grid capabilities. And this gives a whole lot of different applications, including a lot of ways of accelerating development, getting the forecasts out more quickly, allowing us to push to increasingly high resolution and to apply to all these different applications. FE3 is also open developed through GitHub so that people can file issues or add new or suggest new improvements as necessary. Here's an image from our partners at NASA GEOS of carbon dioxide in one of their reanalysis models, partially because it's a very beautiful image, and also, unfortunately, our partners in NASA have much better PR staff than we do over in OAR, unfortunately. So we do have a website for our near real-time configurations. We run 3 of our SHiELD configurations, what we call our tier 1 configurations, in real time, and deliver them to our SHiELD website that my coworker Matt Morin has done an excellent job setting up. We run a couple of different configurations. We run 13-kilometer SHiELD 4 times daily, as well as T-SHiELD 4 times daily, and during the hurricane season coming up here in a few weeks. We also run our C-SHiELD. We also run our C-SHiELD contiguous United States configuration in real time, 2x daily, and we run that out to 126 hours, giving us medium rain severe storm forecasts. One thing I do want to mention, one caveat, is that while we do our best to make sure we can provide data as regularly as possible, this is still an experimental system. There's no guarantees of reliability. We want to be as reliable as possible, but yeah, we can't guarantee 100% uptime. In particular, the computer that we run on, Gaia, is over 100% utilized, and sometimes we end up having to wait in the queue. Plus, we are subject to downtime on both Gaia and our post-processing systems here at GFDL. But you can go to this website to see our real-time forecasts here. Here's an example of a severe weather outbreak from last week, in fact. And this is a multiple day in advance prediction of this very bad severe weather outbreak. This is a plot of the maximum updraft helicity during the entire forecast. And you can see the very high values there throughout the southeastern states, especially in Mississippi and Alabama, where this terrible tornado outbreak took place. Here's a great example of our strategy for model development. And it's a little bit older, but it does show the value of incremental improvements year over year. Back in 2016, which is now quite a ways ago, FE3 is selected for the next generation global prediction system that evolved into the unified forecast system. And once we did that, we were able to start tuning the physics and start to upgrade the physics to be able to get better and better forecasts. Here is precipitation in the tropics and in the contiguous United States. This is the root mean square errors for both, compared to observations and the operational legacy spectral GFS. And you can see that we started out not quite as good as the operational GFS. We started to introduce new microphysics, took new upgrades from our partners, especially at the Environmental Modeling Center. And over year, we improved it to the fact we got just better and better over time. And I like to use this quote from this technology blogger, John Gruber. Incremental improvements every year that seem small, seem like a pretty minimal improvement each year. Over time, it's like the equivalent of compound interest in finance. A little bit year over year turns to do a big improvement 3 over 4 years. It really adds up. And here's an example of more recently what we've been doing. So we developed a microphysics scheme here at GFDL called GFDL Microphysics, originally based on the old Lin microphysics. It's similar also to the WSM set of schemes developed in Korea and here in the US by Song-Yu Hong. We have a number of different new features we implemented within the scheme, upgrading to version 3. The version that's in the current GFS is version 1. And in particular, we found some interesting improvements to the cloud properties in our 13-kilometer shield that we get by introducing some new properties into the microphysics, especially a improved particle size distribution and more realistic background aerosols. And in particular, here in the left-hand panels, you see that by improving the background aerosols, we get a considerable improvement in the liquid water path, as well as changes in the absolute amount and improvements in the precipitation bias. So by doing this, we improve the clouds and radiation, which is certainly an interesting thing, but it's kind of abstract for people who are interested mostly in sensible weather metrics. And indeed, we do see that by improving the clouds and especially how they interact with radiation, we see statistically significant improvements in predictions of 500 millibar height and in temperature at 700 millibars, especially as you go out to longer lead times. Especially in the spring and winter time here. So this is a good example of what we call kind of like climate thinking. I mean, back when I was doing a lot of my own learning about meteorology and the weather, radiation was kind of a afterthought for short time scales, but it turns out that it can have a very big impact on medium range forecasting. So it's not just thinking about like long-term like climate that really depends on radiation, but it's also can have a big impact for short-term forecasts as well. And here's an example I like to give of SHiELD contributing to better operations, development in SHiELD. So back in 2017, after or actually 2018, we implemented a number of changes into SHiELD. We started using the GFS analyses to take a look at tropical cyclone tracks, especially in the very active 2017 season in the Atlantic. So here's a plot of track error here on the left for tropical cyclones again. And we see that we're able, by using our improved SHiELD model, we get the curve in the yellow, we see an improvement in the track errors, a reduction in the track errors. We can go beyond that. We got in touch with, through an intermediary, actually, Fuqing Zhang, introduced us to a couple of folks at the European Center, and they were interested in if we would run with their initial conditions, their analyses, and then give them back the forecast so they could use it to improve their own model. But we could all use it to improve our own model as well. And we found that when you initialize SHiELD with the European Center's initial conditions, we actually got better forecasts than both the GFS and the European Center. And indeed, there is some year-to-year variability in how much better you get, but this did spur a lot of development within NOAA, certainly not just here, but also our partners at the Physical Systems Laboratory, at EMC. They did a lot to introduce the improvements from SHiELD, especially FV3, into and GFDL Microphysics into the GFS. And our partners there, especially those other centers, they really did a lot to improve the data assimilation cycling. And through all of that, they made a huge improvement in the GFS's predictions tropical cyclone track, to the point where in 2021, the most skillful hurricane track prediction model in the world was the GFS, which I don't think has ever happened before. And so this is a great example of R2O, also what the NOAA community is really capable of. And we can go even further than that. We found that actually our SHiELD model, as well as our T-SHiELD model, got even better track errors than any of the operational models. So there's even more good things coming down the pipeline. And this is like what I say, one of the best things about working in NOAA is that I get to work with some of the best scientists, the best engineers, and some of the best forecasters in the world. So it's a really great opportunity and a really great environment for helping to improve just being able to improve forecasts in general. And certainly I don't want to claim credit for all this. This is the hard work of a lot of people throughout NOAA and with our university and other agency partners. So yeah, it's a really great opportunity that we've been given, and we're glad to be a part of it. So now I want to go from traditional medium range forecasting to using our nested grid capability that FV3 gives us to efficiently nest down to convective scales, 3-kilometer resolution, 3-kilometer grid spacing in this case. Yeah, certainly I don't want to dismiss the excellent people who are working on the regional models, like the NAM, like the HER, the RAP, like the upcoming RRFS. But those are really good at very short range forecasts. And the way we like to put it is that limited area domains give limited forecasts. After a few days, the boundary conditions contaminate your forecast. And nothing against the excellent regional model modelers. Nothing against the excellent regional model developers within NOAA and our partners, but that's just a fact of model development. However, we can start to do these global nested models in which we have a two-way nested model, two-way nested regional domain that interacts with this global domain. And we find from that allows the global and regional domains to communicate so you can maintain that large-scale skill out to 5+ days, which then hopefully, and I will show in a minute, that would lead towards better forecasts of convective scale weather and severe weather. And so you see a couple of examples here. One is in the upper right-hand panel here. You can see two versions of SHiELD, one in 2020 and one in 2021, a little earlier, compared to the operational GFS in black and the SHiELD in green. And you see some big improvement in this score. This is the H500 anomaly correlation coefficient between the 2020 and 2021 versions. And the big improvements here is that there are a lot of improvements to how clouds and radiation interacted, especially things like anvils and stratiform precipitation, how the land surface interacted with the atmosphere. We upgraded to a new land surface model, the NOAA MP, on the CONUS domain. And we also made some improvements to the shallow convection scheme as well, to be able to better represent some boundary layer interactions. And through all this, we found a pretty significant improvement in the H500 skill during the month of during the warm season in 2021, which and this I believe is another good example of how to use improvements from the land surface, improvements from radiation to improve your large scale skill and thereby improve your medium range forecasts. So I show another example of this here for the most recent spring experiment period in the lower right-hand panel. You see a variety of models here as well as two versions of SHiELD. And you do see that there is some data run-to-run variability. Yes, do I have a question? Okay.
Yeah, Lucas, I put one in chat there. I didn't want to interrupt you though.
Oh, no problem. I'll answer it here in a minute. Thank you so much. But yeah, you can see both root mean square error on the top of that panel and then ACC in the bottom. You can see some run-to-run variability between all the different models, and you see some cases where the nested SHiELD does a little bit better, maybe does a little bit worse than the global models. But on the whole, you can see that we're able to maintain the large scale skill on the nested domain in this case. And I should point out this is over the contiguous United States again. Okay, so let's see here. So we have a question. Okay, so this is from Jack Settlemeyer. Lucas, have you looked at SHiELD's ability to lessen the GFS's seeming tendency to create too many spurious, strong tropical systems in its day 8+ forecasts? That's an excellent question. So my collaborator, Jianhui Chen, my coworker, Jianhui Chen, she actually published a nice article a couple of years ago on predicting genesis predictions within SHiELD compared to the GFS. And certainly there are challenges in predicting tropical cyclone genesis that far out in advance. My understanding is that actually we have been able to improve some of these false alarms within SHiELD at those longer time periods. I can't say for sure. There's some new results, especially as part of this Dymosa comparison that they're looking at. So I'd have to defer to that. I can send you the references afterwards if you'd like. But thank you for bringing that up, Jack. That's an excellent question. Okay. So, and by the way, feel free to raise your hand or put a question in the chat if you do wish to ask a question. Feel free to interrupt me whenever you like. So some results from medium range SHiELD. So indeed, nesting we have found is extended storm prediction of convective storms. Maybe not individual convective storms, which have a predictability of at most a few hours, but we can start to predict where the threat of convective storms, especially severe weather, may be. So here up in the upper right-hand panel, we have the surrogate severe grids here. The brightest colors represent the highest fraction skill score for a combination of day 1, day 2, day 3, and day 4 as a function of the updraft velocity threshold and the smoothing radius. You can see the highest predictions for a threshold of 75 meters squared per second squared and a relatively large smoothing radius as usual. But the interesting thing here is that we see a fraction skill score that doesn't really degrade a whole lot between day 1 and day 4. And that really indicates that, yeah, there is skill in predicting multiple days in advance in this metric. So that's an exciting thing. And actually, we have a very interesting collaboration I'll talk about here shortly that builds upon that. The other thing we've been working on the last few years is addressing some of these high precipitation biases we've been struggling with in some configurations. We find some interesting impacts on that within SHiELD. So here is a 36-hour precipitation, so a relatively easy metric for us to compute. And this is the frequency bias compared to stage 4 observations. For, I believe this is the month of May in 2022. We have a similar result in 2023 as month of May of 2023. But we have found that the 2023 version, where we've revised the microphysics and shallow convection, as well as made some changes to the advection that we use in FE3 aerodynamical core, has considerably reduced the frequency of too much heavy precipitation that we found in some of the earlier versions, particularly the 2022 version, where we made some changes to the convection scheme that did produce some more heavy precipitation. Had some other improvements, but we realized that, yeah, that high bias wasn't really a good idea. So we rolled those back, and we found a very good configuration that I believe that has addressed a lot of this issue. Okay, here's a collaboration that we're actually very, very proud about, or partnership we're very excited about. So a couple of years ago, our partners at NCAR at M-Cube, their mesoscale and microscale meteorology division, they got a grant from the Hazardous Weather Test Bed to fund a real-time experiments over 3 years using a ensemble of medium-range SHiELD forecasts. And during the spring experiment period, the HWT spring forecasting experiment in May, they did these 8-member, 8-day simulations of SHiELD that they ran on their own supercomputer, and they provided these in real time to their forecast and into the hazardous weather test bed. Analysis is underway, but we did have some really exciting results, as well as some areas where we could improve that came out of this. So, for example, here's one result. This is actually the very last forecast they did that happened to coincide with a tropical storm in the Gulf of Mexico. And this actually did a very good job at predicting the heavy precipitation that occurred not just there in the tropical cyclone, but also the heavy rain in the over that time period in the Texas and Oklahoma panhandles. So this is a really exciting possibilities for what could be done. Here's one example showing both the strengths and the weaknesses of medium range severe storm outbreaks. So in the upper, on the left-hand side, in the upper 2 panels, you see ensemble max updraft helicity. And you see at 144 hours, you see kind of 2 centers of activity where you see some of these kind of like long track events here around in South Dakota, Nebraska, Iowa, southern Minnesota, which turned out to be not too far off from where the tornadoes were reported in this outbreak. And indeed, it was maintained throughout most of this forecast for the next couple of days, to the point where it became more and more precise as time went on. And this could be compared, interestingly, with the SPC outlooks, which is based on the medium range model, especially the ensemble medium range models from NCEP, from the GFS, from the European Center, where, yeah, the predictability was too low to say anything at this lead time, and there was some predictions of a slight chance of a convection of hazardous weather out to 3 days in advance here. So this is an example of a success in this case that does show what you can get by going beyond the traditional kind of proxy approach using the large scale medium range models, and then using convective scale models to explicitly predict systems. Now you can also see an issue here where where SHiELD is also predicting a lot of convective activity in southern Texas here that really did not happen. It's kind of a fizzle event where they only got a few hail and wind reports. And also that is what was looking to be likely from the SPC outlooks as well, which suggests that could suggest a deficiency in our model. One thing I've been dealing with is some of this over convection in Texas for a while. We'd like to be able to dig deeper into this in SHiELD. It also suggests maybe there's something in the medium range models as trying to predict severe weather that just didn't happen. And I have to apologize. I'm not really a severe weather expert, so maybe somebody who does know more could chime in about this. But yeah, there are some interesting facets to this problem, and I'm really glad that we can explore this with our partners at NCAR. We can go beyond the medium range. We can start talking about subseasonal forecasts with the relatively efficient nested grid models. A slightly lower resolution. It's 5 kilometers on the nested grid. You're still able to do explicit prediction of severe thunderstorm outbreaks, making an ensemble of 30-day forecasts in this case. This is done for 5 years of springs, 30-day forecasts. And we did find from the computations of the categorical skill scores that over the northern plains, over the northwest, the Midwest, that there is some promising skill for predicting categorical severe weather activity above normal, below normal, out to weeks 3 and 4. And it was kind of interesting that we saw this enhanced predictability, that's decent skill in the northern United States, where severe weather is relatively rare, or not relatively rare, but it's not as common. There's not the steady drumbeat of severe weather like there is in the southern plains, which kind of suggests to me that simply just forecasting severe weather in any given week in the southern plains is probably a pretty good forecast. It reminds me of these struggles we had with seasonal prediction of tropical cyclones. That tropical cyclone variability in the Atlantic is very big, and there's some predictability there. In the Western Pacific, there's a lot of typhoons every year. So predicting variability, you're predicting one or two from year to year compared to 20 typhoons in a given year in the Western Pacific. And it's kind of the same thing here, and we're predicting subseasonal storms in the warm season. You're going to be getting severe weather in the southeast and the southern plains pretty much continuously. It's rare for there to be below normal, relatively rare for there to be a below normal period. And we started a collaboration with our partners at the National Severe Storms Laboratory with the excellent work that Adam Clark and his group are running. They're going to start looking at subseasonal predictions in the cold season, where there's kind of better predictability of the large scale, as well as perhaps more use to subseasonal predictions in the off season. So this is another exciting possibility we have for working with these people. I'll shift a bit to our tropical cyclone model, SHiELD, which we've developed for tropical cyclone forecasting. This is building on the legacy of the GFDL hurricane models developed for many years by Yoshio Kirihara and Morris Bender, and was operational for 25 years. Here's an example from Hurricane Ida a couple of years ago, showing the threat of extreme precipitation several days in advance. And this is remarkable in this case because, as we remember, Hurricane Ida made landfall in Louisiana, but its biggest impacts are here in New Jersey and in the New York metro area, which is an astounding thing to me, actually. But with this model, we were able to predict some of this heavy precipitation up to 5 days in advance, at least the threat of heavy precipitation. And as time went on, we were able to zoom in a bit better onto the precise track of Hurricane Ida. And there's a number of possible interesting implications for this for both hazard impact assessment. We're working with a couple of partners at Princeton University on this right now. Oh, yes. And then, just circling in on that. One interesting thing about SHiELD, we're using a large static domain, which differentiates it from the excellent HAFS model about to go up to operations next Tuesday, I believe, which is using a regional domain that's 6 kilometers, so still parameterized convection, with a moving nested grid over a tropical cyclone down to 2 kilometers. And we're taking a different, somewhat simpler approach, is to use a large nested domain. And on this domain, we're able to explicitly predict deep convection. So we don't need to parameterize deep convection in these simulations. And this is kind of a double-edged sword. I mean, everybody complains about convective parameterization. I'm one of those people who doesn't think they're particularly great. And indeed, that's one of the kind of issues that goes on with medium range prediction model and with subseasonal prediction models. Kind of a necessary evil, more or less. But now that you have the power to represent explicit convection and do the heating and moistening instead of the parameterization, well, now you have the responsibility of doing that well. And on top of that, you can't tune explicit convection the way you can tune a convective parameterization. So the question is, does it have the right effect on larger scales? So we did this interesting experiment. My colleague Kun Gao, who leads development of SHiELD, there's this article we got in review at GRL. He used 2 different configurations of SHiELD with different advective schemes with different diffusivities. And he took a look at the updraft densities in those simulations. We found that this scheme right here, which is somewhat less diffusive, and this producing these weakly forced convection over the warm tropical Atlantic, it produced a lot more convection then did a slightly more diffusive scheme here that we use for real-time simulations. And this actually has some interesting implications on the subtropical high. We find that when you have more convection, it does distort the shape of the subtropical high, which is something you don't see in a relatively coarse resolution like a traditional SHiELD, where we have to parameterize convection instead. So this is kind of the gift and the challenge of convective scale prediction, especially when you get to larger and larger domains and longer lead times, because this shift to the subtropical high, it's going to affect your tropical cyclone steering flow that you wouldn't have, an effect that you wouldn't have at traditional parameterized resolutions. And this is then going to affect your tropical cyclone track forecast as well. So this is an interesting thing. I've been trying to get more people to think about this interactions of explicit convection with synoptic and planetary scales. It's an interesting challenge, especially move on towards larger convective scale domains. Here's a really cool thing that we're really excited about. So a few years ago, I was giving a talk at the European Center, and Tim Palmer, who was a professor at Oxford, used to work at the European Center. He saw about me talking about my nesting. He said if I really want to improve forecasting over the contiguous United States, instead of putting a nest there, try putting a nest over the maritime continent and improve your MJO predictions. And now we've actually done a pretty good job with MJO predictions. Our SPHERE seasonal to decadal model get very good MJO predictions, even at 100-kilometer resolution. And as you go to 50, 25, 13-kilometer resolution, you get better and better forecasts. You don't need the high resolution to get an MJO in the first place, but it does make the MJ forecast better. So we have this collaboration using our nested grid with our partners at AOML. And we started doing these 40-day runs with a 16-kilometer global domain and a 4-kilometer nest over the maritime continent here, which is where kind of a critical area for the MJO. It's tend to be where it gets stuck in a lot of traditional weather and climate models. And we found by putting in that nest, we extend what was a decent MJO forecast out to a very good 39 days of useful predictability. And we find out this is because by putting in that 4-kilometer nest, we're able to improve the diurnal cycle of convection over Indonesia and Malaysia. We're able to improve the moisture transport, which improves the mean state, and thereby MJO propagation. The propagation gets out onto the out beyond the nested grid and into the global domain. And now we're starting to do analysis of the whether we can improve teleconnections by doing that as well. I've been mentioning by convective scale, we go to about 3-kilometer resolution. This is the same as the NAM nest and the HERB as a forthcoming RAP. We want to start thinking about, can we go farther than that? Can we start to go towards increasingly high resolution to get you better, very local impacts, being able to get predictions of even increasingly small scale features? And we have a new model taking advantage of our new multiple nesting capability called SHiELD that nests down to 1.4-kilometer resolution over a relatively small area. We've done a couple of experiments. We participated in this field campaign called Precept 22, where we submitted real-time multi-nested forecasts over Taiwan, which is where this field campaign was taking place. We also are developing a Northeast Corridor nest. We want to start running this in real time, hopefully later this year. We could consider other domains of interest as well, say the Great Lakes, the Front Range of Colorado, any number of different areas that might be of interest if people are interested in collaborating to develop a version of this. And then beyond that, we want to start going down to even higher resolution. We want to start going down to these sub-kilometer domains, in which you start to resolve the large eddies of turbulent flow. You start to resolve entrainment in convection and so on. And this is useful already for process modeling. I show a couple of examples here. This is a radiative convective equilibrium experiment, useful for testing parameterizations or ideas about convection. We can go even further. We did some tests at 35 meters of forced shallow convection. This is a common way of evaluating large eddy scale models. We're developing a turbulence parameterization for this. And then we could even think about like large eddy scale prediction. I know the UKMO has an excellent 100-meter domain over London that they used originally for the, I believe it was the 2012 Olympics. They use it a lot for fog prediction, but there may be a lot of impacts here for urban scale prediction, for aviation, and so on. Here's one cool example of this. This may not necessarily have a forecast application, but I thought this was kind of neat. A while back, we started doing these experiments where we use our stretching capability in FV3, where you develop a simplified model. We stretch the global domain into a truncated pyramid. In this case, you're doing a lot of stretching to get efficiently over to 1 kilometer, 500 meters over a small patch of the Earth. And we did this directionally sheared supercell test and started to develop asymmetric supercell thunderstorm that had these kind of interesting phenomena extending out beneath them. They're larger than real tornado vortices. We call them tornado-like vortices. But we do see that they are dynamically like real tornadoes. They are just created by distinct dynamical processes, the tilting and stretching that we see in real tornadic vortices. And it's kind of interesting. We see this at what is considered relatively coarse resolution for this. So I thought this was a kind of cool thing, and really also shows kind of the value of emphasizing vorticity in your discretization, which is one thing that we do very strongly. The final thing I want to talk about is our global storm resolving model, which is becoming all the rage in some quarters lately. We've actually gotten a hop on this. We have this is the latest in a 15-year series of GSRMs developed between GFDL and NASA Goddard using the FE3 dynamical core. SHiELD, our experimental system for high-resolution prediction on Earth local domains, is a global storm resolving model, no deep convective parameterization, so it's all explicit worldwide. But despite that, we are able to run this out for years continuously. We've run out to 2 years and 6 months, I believe, so far, 2 years and 3 months, actually in a variety of climates, as well as we've done experiments with 10-day initialized predictions. This is still too expensive for routine simulation. So right now it's mostly of scientific interest and of a technical demonstration. In fact, we were able to get this model to scale out to the full size of our new partition on Gaia, 221,000 cores, to get 8.25 minutes per day. With the full model, we are dealing with some load balancing due to the physics, simply having to do different things in different parts of the world. But we think we can improve the scaling as well. And when it comes to this, I really like the saying of Suki Manabe, who is a meteorologist here at GFDL for many years and won a Nobel Prize in Physics for his work on climate science a few years back. I like the way that he puts this. If you keep increasing resolution but don't make the model more complicated, I think you will have a great time. And certainly there's a lot of value with adding composition like aerosols, a lot of ecosystem things, chemistry, and so on. But for this purpose, we want to try to get as much efficiency as possible to be able to get just raw throughput to really explore what you can do with these resolutions. Here's one example of what you can do with a global storm resolving model like SHiELD. You can use it to feed these hungry machine learning algorithms that are all the rage nowadays. And here's an example. Our partners at the Allen Institute for Artificial Intelligence in Seattle, near where I went to graduate school, they developed this really cool hybrid dynamical machine learning model. They run this at 200-kilometer resolution, very coarse by any standard nowadays. But then what they do is they're able to correct this model against the SHiELD output. They train a correction on the nudging tendencies to our 3-kilometer SHiELD output. And by doing this, we're able to apply this machine learning correction to the physics. And by doing that, we're able to significantly improve land precipitation, diurnal cycle, and surface temperature, both in long-term simulations and also in 10-day forecasts they shown in a previous paper. And this is really cool because you're getting these big improvements. With the model, it's literally 10,000 times less expensive than the global storm resolving model. So this is really opens a lot of possibilities for large ensembles to really get a good idea on variability and uncertainty in your forecasts or in your climate simulations. Finally, I want to describe a lot of what our community partners and ourselves are up to with developing an FE3 and as well as in SHiELD. I don't want to go over a lot of these things, and a lot of them are very technical, but I do want to show that this is the value of our excellent community. I get to work with excellent scientists both inside and outside of NOAA. I really like this quote again by my retired colleague Morris Bender. A key element that makes collaboration successful is having individuals who enjoy working together and are able to do so. And he did this in the context of the GFDL hurricane model and in terms of HWRF, but I think this is more broadly generalizable, that you get people who are really good at working together, you can really achieve some really cool things. And before I wrap up, I want to just pose some discussion questions I like to the audience. And here at GFDL, I mean, we're in a very kind of a scientific, kind of a academic ivory tower environment, I have to admit. And I don't have a whole lot of background in operational forecasting myself, but it would be interesting to see what would forecasters find useful from these models. I mean, what would they find most useful from a convective scale, medium range, or subseasonal prediction model, for example, like T-SHiELD or S-SHiELD or T-SHiELD or C-SHiELD we're developing. And beyond that, even if we do have an experimental model, I know from my time at the spring experiment a few years ago that there's this colossal torrent of model and observational data for forecasters to look at. So the question is, how can we make an experimental model useful for forecasters? And I don't want to just shove all this data onto you, because I mean, yeah, you've got I understand forecasting is a very difficult, time-constrained activity, and I don't want to just cause more problems for everybody. So how can it serve forecasters? How can the output be made most useful for forecast applications, and perhaps better interactivity, providing the binary data so you can put it in AWIPs? And beyond that, it's just also, I'd love to be able to open it up to all of you to really hear what kind of things might this sort of model be able to help you with. And finally, to sum up, I want to thank the excellent team that I work with, the FE3 team, as well as our partners out in the community, as well as our former leader, SHiELD, creator of FE3 and SHiELD, who's really achieved all this. And I really like the quote by Steve Jobs, not just applicable to our team, but to the general weather enterprise altogether. There are no shortcuts around quality, and quality really starts with people. And I'm really grateful that I had this opportunity to talk to all of you, and glad that I can talk to some really great people who are doing really great service for the nation. So thank you, and I'll take questions now. Thank you so much.
Thank you, Lucas. Great overview of SHiELD. So thanks for putting that slide up. If you have any questions or have any answers for the discussion question slide, please raise your hand or put it into chat. Brian, go ahead.
Yeah, first off, thank you again, Lucas, for agreeing to come to this meeting. I think it's been really useful for us to use the data. One of our forecasters here started showing it to us. And
wow.
That's one thing I wanted to get from you is I think you need to advertise it more. It's just because one forecaster may have found it. I don't know if it was with an HWT or some other source, but we had no idea that this was even out there. And I know as an office here, we've got maybe 5 or 6 forecasters that look at it regularly. And for medium range, to be able to see even convective mode, just looking at the composite radar reflectivity, we don't get that type of a high resolution forecast beyond the HREF, your 48 hours. So to be able to see something coming, you can, plan staffing. You can see, hey, we may have some QLCSs coming through, some discrete cells, whatever it is. That's something that'd be most useful for us.
Oh, well, thank you. Yeah, I'm very, very flattered to hear that. Yeah, that you do find it useful. I mean, thank you so much. And I'm sure that, OER management would be very glad to hear that. I mean,
but make sure and advertise. Yeah.
Thank you. Yeah. I mean, definitely. I'll definitely try to see about talking to more people about it. But thank you so much. I'm really, really grateful to hear that. Yeah. Okay. So let's see. I believe Jack and Brett. I'll answer Brett's question first. Most helpful is higher resolution model output, 1 kilometer, in areas of complex terrain like the Western U.S. Okay. Yeah, that's wonderful. And I mean, complex terrain is something we are interested in, and there's a fairly broad. The Western U.S. is a fairly broad region, and 1 kilometer would be fairly expensive this time. But it does help guide, where we might be most useful. I know that there's been experiments in a couple of areas in the West to that extent. Is there any particular, if there's a particular area in the Western U.S. that would be useful, or perhaps even relocatable, that might be a very, very interesting thing for us to take a closer look at. But thank you so much, Brett. Jack?
Yeah, Lucas, thanks for the presentation and all the great details. This is the deepest I've seen into SHiELD. I saw it somewhere else, but this is a lot more. So thanks.
Thank you.
I guess the one comment I had, you mentioned earlier the hazardous weather test bed that I think your output is flowing to. Is that correct?
That is right. Yeah.
Have they done? I'm looking at your website and trying to, there's always improvements on websites that could be made. Right. But I was thinking about some of the verification variables that some groups show would be helpful to know, how well some of the output has done on some of the future forecasts.
Okay.
Is there any of that exists on the website, or could there be, or did the HWT work any of that up to be
Okay.
able to peruse?
Yeah. So I mean, I know the HWT, they have a very, they have a phenomenal website, I have to admit. I don't even have to admit it. Yeah, it's great to work with them, and it's really great to see what they do with it every year. And we don't have quite that level of sophistication yet on our SHiELD website. But if there is interest in like real-time validation to show the reliability of the forecasts, that is a possibility. I mean, we do some internal internal validation to get a good idea of our skill. But yeah, like I said, if that is a good metric of reliability, it would help forecasters. Then yeah, we can talk about making that publicly available as well. One thing that we do have is like for tropical cyclones in both SHiELD and T-SHiELD, we do after the fact go back and plot the tracks of storms that go with it, as well as the validation of the intensity. So we do have some limited capability in doing that, but we haven't expanded upon that. But it is really neat to know that, yeah, people would find that useful. So we can see about adding that to the website. Thank you so much.
And I guess towards that, I was looking, the T-SHiELD looks like it's only from 2022. Will there be any current runs of that, or is it not running currently?
Absolutely. I mean, we found out that, in fact, we just were told today that we got a real-time reservation on JET to be able to run T-SHiELD in real time on a reservation to make sure that it can be supplied in near real time for the upcoming hurricane season. I believe it starts in a few weeks here. So we typically only run T-SHiELD during the hurricane season, since it's the principal focus, although we would be interested in running it towards the cold season as well. I know that there's the folks at WFO Honolulu who were actually interested in using it for high seas forecasting. So that's an interesting possibility. We'd have to find the resources to run that, but that is something cool that we could do. Yeah, but thank you.
Sure. And one last one. You mentioned NOD on one of your slides, and it looks like I see SHiELD has some output there on Google.
Mm-hmm.
Do you have any of the other outputs besides the SHiELD?
We haven't put anything up there quite yet. There has been some talk in the past about putting our making our real-time data available through some sort of feed. And if the GRIB data would be available, like I have to apologize, Brett, I missed that. But if we did want to make the GRIB files for our models available, we could make it available through a steady stream on NODD, which would be a good way for people to easily access and use it if there's that desire for it. But yeah, so as yet we haven't gotten around to doing that, but it is certainly a possibility, and we should be able to get more space in NODD simply by just requesting more space in the cloud, which it's a phenomenal service, and I wish it was easier to get more data onto it.
Yeah, and towards that, the SHiELD is great, but I think for a lot of the forecaster purposes, to have the C-SHiELD output there would be helpful.
Oh, great. Well, thank you so much. And yes, I do want to point out, Brett, that yeah, we usually do output in NetCDF, but we do convert to GRIB for the spring experiment. We could conceivably continue to do that for year-round applications as well. Thank you for bringing that up. So Ryan asked about getting C-SHiELD merged into href. My understanding is that href is more or less frozen right now. The expectation is that the RRFS ensemble will replace that with a relatively more uniform model, the kind of the way the NCAR ORF ensemble was run. Let's see here. So that's basically the upshot there. There hasn't been any effort to merge it into href, partially because href is kind of more or less end of life at this point, to my understanding. The hope is the RFS ensemble will replace it, thereby simplifying it. But thank you for bringing that up. Thank you, Ryan.
All right, seeing no further questions, Lucas, I'd like to thank you again for presenting, and also like to thank everyone for attending this latest guest speaker series. Thanks again.
Yeah, thank you so much, everybody. This is a fantastic experience, and thank you so much. So glad to hear people enjoy our models. Okay, thank you.